let's start. So we now come to the maybe more advanced theoretical part of these lectures. We would like to prove order of convergence estimates, more precisely a priori order of convergence estimates. That is, we would like to estimate the deviation between the unknown exact solution of the continuous boundary value problem we are looking at on the one hand side, that is of u, and of the approximation, the finite element solution we are computing, that is UH. So we would like to estimate u minus UH. So first thing is we need an appropriate norm. So we need a norm which such that u and UH both belong to the corresponding space. And of course, the stronger the norm is, the better the estimate is. So an L infinity estimate would be better than an L2 estimate. An H1 estimate would be better than an L2 estimate. There's some relation between H1 and L infinity, as we know in one dimension. Okay, so what can we do? And it's an a priori estimate that is, let's see whether we have it somewhere here. That is, we would like to prove something like that. There is a constant depending on the problem, on all the parameters of the problem, geometry, whatsoever, on the solution only in terms of a semi-norm, which we want to specify later on, such that we can estimate this error by this constant times the semi-norm times a certain power of h. H is the discretization parameter which we have. So typically in our case, in 2 dimensions with triangles, it would be the maximal length of an edge, or in general, it's a diameter, the maximal diameter of all the appearing elements. So the H indicates how many elements we have, how many degrees of freedom we have, how large the problem is. So there's some relation, some inverse relation between the smallness of the H and the size of the problem. And of course, we would like, the smaller the H, the more effort we have to do. And of course, we would like to have this reflected in the smallness of the error. The first thing, of course, we would like to know that the procedure converges in principle. That tells us that at least asymptotically what we are doing is correct. And then, of course, that would be a proof of convergence in a certain norm. An error estimate, an a priori error estimate, tells us more. It tells us how the error behaves in the worst case, for example, if we halven the H. And then, of course, the order power here plays a role. So 1 would be a typical case, but 2 is better than 1, and 3 is better than 2, and so on. Okay, so which kind of norms? That is, they're opposite to these a priori error estimates, there are also a posteriori error estimates. Before coming to saying something about these, maybe we should think about this constant here. In some simple cases, we will be able to compute this constant c. But here, we will not try to do so. So we have no idea how big or how small this constant is. So typically, it's big. What we have seen already, that one important ingredient of this constant is this quotient m over alpha. M being the boundedness constant from the continuity of the bilinear form, and alpha being the constant from the V ellipticity of the bilinear form. So this and Thea's lemma tells us, or at least the way doing these error estimates via Thea's lemma brings in this quotient. And of course, this means if this quotient is large, then in any case, we have a large constant there. Later on, we will look at situations where this quotient is large, and typically this will be if problems become convection dominated. If the convective part, the first order part, is the dominating part compared to the second order, to diffusive part, then this alpha is small, and therefore m over alpha is large. That does not mean that the methods, all the methods we are discussing here, are not convergent anymore or do not have this order of convergence which we are proving, but it tells us that there might be situations where this constant is astronomically large. That means that, practically we can only compute with a finite age. We can only compute with 10,000 or 100,000 or 1,000,000 nodes reflecting a certain age. And that could mean that we are still far away from any numerical convergence in such cases. There is convergence, but it would require such an astronomical amount of degrees of freedom which we cannot afford. So practically, the problem then comes to a certain end. But theoretically, still everything is convergent. Even in cases where it's extremely convection dominated, if you have, I think we spoke already about the Pickley number, if you have enormously large Pickley numbers. Okay, so this is a problem to which we will come later. At the moment, we just assume that those constants are in a reasonable range, and we do not care too much about them. Now we have to decide about the norms in which we want to prove the error estimate. And as I said, of course, the stronger the norm is, the more the error estimate tells us. But we know already that in conjunction with the finite element method, there is one natural norm we are heading for. Namely, that's the norm of the underlying space, here in our case the H1, so the H1 norm, the space in which the bilinear form is continuous and it's V elliptic. Or in the special case where the bilinear form is also symmetric, so forget about the convective forces, that would just mean we have a norm which is equivalent to the energy norm. And therefore, these types of estimates we are now going to prove are also called energy estimates, or energy norm estimates. Of course, then there are two questions then related. The one is, can we say something about the L-infinity norm, which we have seen already in conjunction with the finite difference method, but with a lot of assumptions in the definition of the method, in the regularity of the solution, and so on. And this is a very, very difficult problem for finite element methods. There are L-infinity estimates, but I will not touch on that. And there's the easier question, namely the question, what about L2 norm? We go down from an H1 norm to the L2 norm, and of course we would expect that then the convergence gets better. Of course we know it's the same kind of convergence because it's a lower estimate of the norm, but we would expect to get more than by only looking at the L2 norm. This is a problem which we can address, which we address then after having looked at the energy norm estimates, but we cannot do it via Thea's lemma. Thea's lemma only tells us something about the H1 norm, about the norm in which the underlying problem is coercive, is V elliptic and continuous. Okay, so I think I have said basically all the things which we have to do. So the framework is the framework which we now defined. We have now a domain in Rd, a bounded domain in Rd, subdivided in a conformal triangulation Th. Actually, it's a whole family of triangulations. We want to see what happens if H goes to 0. And we use certain elements which are characterized not only by the spatial elements capital K from Th, but by the ansatz space Pk. We have seen this is typically a space of polynomials in the simplicial case, or is a transformed space of tensor product polynomials of Qk in the transformed unit cube case. And we have our degrees of freedom, sigma k. And what we would like to take advantage of is that we, and that is of course also necessary, that in the end in some sense necessary that we have a conformal triangulation, that those triangulations not only fit together in terms of elements, but also fit together in terms of degrees of freedom at the corresponding boundaries and in terms of Ansatzspaces. So one possibility would say we choose just one type of elements, which are all affine equivalent, in particular affine equivalent to one reference element. For example, we only use triangles and we only use quadratic ansatz at the triangle. That would be a typical standard finite element method. We have a little bit more degree of freedom. We have seen that we can mix different approaches. So we can combine, for example, triangles with quadratic ansatz space with parallelograms with biquadratic ansatz space. And this is meant here, so we have an finite amount of subs, so we have a independent of h, the triangulation is subdivided in a fixed finite amount of subsets, and each of these subsets is in itself affine equivalent. So in this case we would have two subsets. The one is the one with the triangles with the quadratic ansatz, and the other is the parallelograms with the biquadratic ansatz. And doing so, in the end, our ansatz space VH is well defined, saying we glue these elements together, and they are well defined by their degrees of freedom, and they become continuous functions, and by this they become functions in H1. So we have VH equals V, which is the important assumption for our conformal finite element approximation. There are also other finite element type approximations which do not require that the ansatz space VH is a subset, is a subspace of the underlying space, but this requires then another theory. So for us, this was enormously important to have this, because this is just the reason that we have this error orthogonality, that we have this equality A applied to the deviation, A U minus UV, U minus UH, tested with any function VH from the finite dimensional space is 0. And this is the basis, as we have seen, of Sear's lemma and so on, which is the basis of the whole error analysis. So to make the things simpler, in the following, we explicitly only deal with one type of element, all affine equivalent to a reference element, and this generalization, which I indicated, I think will become clear from the analysis. So this is the type of estimate we are heading for. This I explained already, and of course, everything which is connected with that we discussed already. Maybe I should still make a remark on the notion of a posteriori error estimate. In the a posteriori error estimate, this is an estimate for the error, maybe also with a constant, but with a constant which is then well known, times something which depends on the solution. And of course you can say, okay, what kind of nonsense is this? Why should I estimate the error by after knowing the solution? Of course, it's not a nonsense if you do not think of exercise problems. In a typical problem, you don't know the exact solution. But having the possibility in saying how large the error is, and not only globally but also locally, so an a posteriori error estimate gives this type of estimate not on the full domain, but on subdomains, typically the elements, we can say, okay, on this element the error is large, and on this element the error is small. And this gives us then the possibility to do refinements related to this estimate of the error. And then we come in the range what is called adaptive triangulation, adaptive refinements. That is something we will touch on maybe later on a little bit. Okay, so keep in mind that we don't have a fixed family of a fixed triangulation, but always a family of triangulations for h2, 0. So we have to distinguish between variable quantities and fixed quantities. So the variable quantity is, of course, the h going to 0, and related to that, the m of h, which denotes the amount of degrees of freedom, the amounts of nodes we have, which then correspondingly goes to infinity. On the other hand, we have some fixed quantities. For example, the dimension d. It's a pretty small number, 2 or 3 in our case. Or we have the dimension of the ansatz space. It's also a fixed small number, say 10 in the biquadratic case of triangular. That is, in all the situations where we have fixed quantities, we have, so to speak, small finite dimensional spaces with fixed dimension, we can, first of all, we can free in choosing the norm, because we know for finite dimensional spaces, for a fixed dimension, all norms are equivalent, and we get certain equivalency constants. All these constants then enter up in this generic constant C, and all these other fixed quantities, we are free in having them entered into this generic constant C. Of course, we always have to make sure that this constant is independent of h and equivalently of m of h. Okay, so now we are looking for energy norm estimates, as I said. So the norm we are looking for is the H1 norm, and Sear's lemma tells us the estimate between u and uh is up to this constant m over alpha, as good as the best estimate I can find in this finite dimensional space Vh for my unknown solution u. So the only thing we are from now on only concerned with is, so to speak, the approximation error, which we get approximating a general function. Let's call it now here u. Later on, it's the solution of the boundary value problem, a general function u of v by a function vh in this finite dimensional space. So we have to look for a good approximation and then estimate the error of this good approximation. Okay, what we are going to choose is going to choose the interpolant of this function. And taking this is this notation IH of u. And choosing the interpolant, of course, requires that our function u has to be a continuous function. And this requires a certain basic regularity assumption we have to do for our solution. Our solution is, by definition, only an H1 function. Only in one dimension we know that an H1 function is continuous. In the other cases, it might not be the case. So we need more. But we know if we have an H2 function and restrict ourselves to 2 and 3 dimensions, then H2 functions are also continuous. So this is the basic regularity requirement which we do from now on. The function we are approximating, later on the solution of the boundary value problem, has to be an H2 function. This might not be the case for all possible solutions or in all possible situations, but of course it's a much, much lesser requirement than all these requirements we had in the finite difference analysis with C4, CA, C something. Okay. Okay, so in the following, so we have discussed both Lagrangian elements and we have discussed also Hermitian Lagrangian elements which have values as degrees of freedom, and Hermitian elements which also have partial derivatives as degrees of freedom. We now restrict ourselves in the notation to the Lagrangian elements, but that's only a sort of a simplification. There's one place where there's a deviation. Maybe we'll see this one place. But let's first stick to Lagrangian elements. As said, also Hermitian elements are not so much in use anymore. And then maybe we'll see where we have to do something different. So what is the notation? So we have a triangulation. This triangulation has certain nodes where the degrees of freedom are positioned, A1 to AM. Of course, for h going to 0, this m goes to infinity, and correspondingly we have the nodal basis functions phi 1 to phi m. So globally written down, the interpolation function is just this quantity. It's a linear combination of the nodal basis function, and the coefficients are just the values of u at these nodes. So this says this function has exactly those values at the nodes, and this, looking at a linear combination, says we are in the finite dimensional space. Okay, and we define I said we need at least H2, and we phrase this in this form. We require that U is in HK plus 1, K greater or equal to 1. And we will see how this K then will reappear in relation to the method we are analyzing. Okay. So we know in this restricting ourselves to d equals to 3, that means we are at least in H2. That means the interpolation function is continuous. That means the interpolation function is an H1 function. So we can look at this quantity, u minus IH of u. And our aim now is to prove that this approximation error is of the order C alpha. More precisely, we want to prove that there's an estimate by some generic constant. The alpha power, a certain alpha power, the alpha has to be specified, of h times the k plus 1 half norm of u. And note what is of importance, also of importance for the derivation of the estimate, is that here we only have the highest order half norm, not the full k plus 1 norm. So it's only the highest order derivatives which appear here. This is indicated here with this 1 bar, that's the half norm. The 2 bars is the full norm. Semi-norm, I should possibly say in English. Halb norm, semi-norm. Okay. So let's have a look at this semi-norm. So here again you have the definition. What is the semi-norm squared? We only look at the derivatives which have where the multi-index alpha has the corresponding length L, not less or equal than L, but equals to L. And now we can play a little bit around here with the formulation. Of course, the first thing is what we will see and what we will use. We want to estimate integrals. And integrals are sums over integrals over small subdomains. Here in our case, we take the elements. So we can break down the questions of estimating these quantities to looking at the quantities at elements. It's very similar to the assembly process. So this we do here. We break this up in the integral over all the elements. We sum over all the elements and have here the integral over the individual element. And then you see what is here is now again a semi-norm, but it's a semi-norm only on the domain K. And if we have here a different domain, a part of the domain omega, we indicate this here in the index. Actually, we must here a slight, this is not really precise because K, we always say K is a bounded, is a closed set. And for the definition of LP spaces, of Sobolev spaces, of course, we should have open sets. So to be more precise, I should have written here the interior of K. So leave away the boundary. But to make the notation a little bit simpler, we just write it in this form. So what we see here is that first of all, we can subdivide the semi-norms in all the semi-norms over the squared in all the semi-norms over the elements, and correspondingly we can do this with the full norm. So this is the first step, which tells us we can, looking for an estimate for the global integral here, we think of everything squared to get rid of the square root here in the definition. We can break this down in local estimates on each element. Okay, now we need a little bit of notation to indicate that we go back and forth in this global and local formulation. Okay, so on the one hand side, we have the global interpolation operator IH, and of course also on the element K, we have also an interpolation operator, which is now denoted by IK. So what does this thing do? It needs the nodes which are related to this element K, which here are denoted by AI1 to AI capital L. So L is a fixed number in our case because of this affine or because of the equivalency of the elements. Say 3 or whatever, 3 in the most simple case, or 6 in the quadratic case. And we have the corresponding positions for the degrees of freedom. We have the corresponding values here, and here these are then now the local basis functions, the basis functions which we then have called shape functions, Formfunktionen. So this formula is, now what is the relation? The relation is we have a compatibility between restricting to the element and doing the interpolation. That means it doesn't, we get the same result either by doing the global interpolation and then restricting to the element, or restricting to the element and doing the local interpolation. And to do so, the only thing what we have to check is that this function here, which comes out here, is the solution or is a solution of the local interpolation problem, and then it's the solution. Because we're always in a framework where the local and then the global interpolation problem is uniquely solvable. Okay. So now we're now in a position that we can go down to an element. So what in the end we would like to have? We would like to estimate u minus IKU, in principle in the one norm, by C times H alpha, and then the semi-norm. And we go now a step further. We not only want to estimate the one norm, we want to estimate all m norms between 0 and k. This is a reasonable question to pose. How good is the approximation error in different norms? Only the one norm then further on helps us. Only for the one norm, for the H1 norm, we have a relation between the error, the finite element error, and the approximation error via Sayre's lever. We don't have this in the L2 norm. So if we get here an estimate for the L2 norm, this does not help us immediately telling us, okay, also the L2 error in the finite element method is of the same order. You don't have a Sayre's lemma in the L2 norm. Be careful with that. So how do we prove now this type of estimate and figure out what the alpha is? Yeah, it's very similar to what we did in the assembly process. You can imagine what we are doing is we have here an integral to estimate, an integral over the domain k. So first we transform to the reference element k hat. The assumption of affine equivalency comes in here. Then we prove this estimate on k hat. And on k hat, this estimate becomes a very specific form, because on k hat, dh is just dh of the reference element. It's just a fixed number. For example, on the, what is dh hat for the triangle reference element? No, it's a maximal length. There's a longer edge in this. Square root of 2, yes. But it's also a fixed number. Okay. And then, of course, if we have this, we have to go back. And this process of going to the reference element and going back in some magic version will us produce these powers of h. This we will see. Okay, so we have to distinguish a little bit between the global h and the local h. So in each element we have an hk, which is just the diameter of the element. So for the reference triangle, it would be square root of 2. And then we have the global quantity, which is just the maximum over all those quantities. Of course, if we have estimates, local estimates, which come up here with an hk to some power, of course, we can always then estimate from above by h to some power. So we forget about this local variation, which is in the fineness of the triangulation, and maybe in this local variation in the error which we see there. We could do that, but we also can keep this variation. Okay, so let's do this. We assume that we have a reference element k hat, which has L nodes, A1 hat to AL hat. So this is now fixed. And all the elements we are looking at are affine equivalent to this reference element. That is, for each element, k, we have this affine linear mapping from k hat to k, which we have used already in the assembly process, which, as the D has just one of the nodes, one of the points as reference, say A1, and the other, the columns of the matrix B are just the connecting vectors to the other points. By this transformation which we now have, we have sort of a pullback. So a function which is defined on the general element k can be pulled back to the reference element. And this is denoted with this notation. So if I have any function v on the general element k, I can attribute to this function a function v hat, now in x hat, by first going back. So what I do, I'm at x hat, I go to the corresponding point in k, and then I apply the v. So, and if I do this, for example, I have the interpolation operator on the element k, and I do the same thing. So I write this back in the coordinates of the reference element. Then it turns out this is just the interpolation now on the reference element of the function pulled back to the reference element. And again, we only have to check that these two functions, they are both functions of the same finite dimensional space of our P ansatz space, and the only thing which we have to check, both solve the same interpolation problem, and then they have to be the same. Okay, in this way we have a relation between the shape functions on a general element, that is the nodal basis function restricted to this element, and the shape functions on the reference element. Often one only uses the notion shape function only for the reference element, but in this sense it doesn't make too much sense. We have seen on the reference element the shape functions, for example, on the reference triangle was very simple. That was, what was it, x, y, 1 minus x minus y, I think. And correspondingly, we have the same thing transformed, and that is then just the corresponding nodal basis function restricted to this element. So, doing now this transformation process, of course, we have seen already in computing those integrals in the H1 norm, and here now we said we would even like to do this for higher norms, maybe. Also, the H1 norm is the most important one. We have to do two things. We first have to transform the integrals. Then we get the determinant of b as the transformation factor in the thing. And then we have to rewrite the derivatives, which are derivatives in x, has to be rewritten as derivatives in x hat. So we have to use the transformation and have to use the chain rule. And what comes out, as this we have computed already, it's the same thing if I take the x gradient This is now the gradient, so this is the derivative written as column. If I take the x gradient of v and apply it at the point f of x hat, or if I take the x hat gradient of v hat and I have to multiply this in front with b to the minus d, so the transpose of the inverse of b. This is just a chain rule, and this computation we did already in conjunction with the evaluation in the assembly process. The problem a little bit is if we now go to higher derivatives, at least in multiple dimension, it becomes more complicated, because higher derivative. So what is a derivative? A derivative is a linear approximation. So it's a linear operator which approximates the nonlinear operator locally with a certain accuracy. Exactly what the notion of differentiability says. What is now a second derivative is a bilinear operator, and so on and so on. So things we do not see in one dimension. In one dimension is always a number. That becomes now apparent in multiple dimension, and we have to be, the computations become a little bit more complicated. Therefore, I've written it only down for for the second derivative. The corresponding formula for the second derivative is, so the second derivative in x, so that would now be this matrix representing, so this is a column, where the corresponding row, the transposed thing, is representation of the linear mapping. And here now we have a matrix which represents the bilinear approximating mapping. And this matrix here is the same as if I do the computation in x hat, but I have to multiply from left with b to the minus t and from right with b with the inverse of b. So this is again a just chain rule, Kettenregel. And corresponding chain rules also hold true. This is now the situation, so to speak, for H1, for H2, and corresponding chain rules hold true for higher order Sobolev spaces. But I do not dare to write them down. Okay, to make the things simpler and to get some orientation, let's first restrict ourselves to the one-dimensional case. And let's see what is the situation in the one-dimensional case. So in one dimension, of course, finite elements are not so complicated, not so interesting, not so something. Elements are just, what are one-dimensional finite elements? Okay, we have simplicial elements. No, that's not one dimension. That would be the basis function. And the element, the spatial element, is just a subinterval. And then we have, say, P1 would be those what is called the head function, and corresponding, if we have more degrees of freedom, more nodes in the element, we get more and more higher order polynomials. That is the one-dimensional situation. Okay, so in the one-dimensional situation, all this business with the reference element and so on, in some sense, is not necessary. But similar to what we did for the assembly, or for this problem of the existence of the interpolation operator, we do now the same thing. We now do a complicated proof in the one-dimensional situation and see how this goes over to the multi-dimensional situation. So we do the transformation to the reference element. So the element is just a subinterval with these two nodes AI1 and AI2. Here we have the reference element, which is here taken as 0, 1. Of course, one can also take -1, 1, or whatever. I've taken here this one. This fits in the sense that now the transformation is just hk, the length of the interval, times x hat, and then I have to shift the whole thing that it starts at this point here. It's this formula we have from d dimension just applied to one dimension. Okay, now here, of course, now to compute the derivatives and also the higher order derivatives is now pretty simple. If we now have here, want to compute the x hat derivative, if we compute the x hat derivatives of this composition here, so what is this composition? This is v of f of x hat. So first we have to compute the x derivatives, and then we have to, in the chain rule, we have to compute the derivatives of f, but each derivative of f only gives the factor hk. So we get, so to speak, in the first derivative, L equals to 1, we get an hk on this side, the second an hk square on this side, and so on. Or put it to the other side, we get this formula here. Now the determinant of this mapping, okay, the determinant of a 1-by-1 matrix is also not so complicated to compute. So this is hk here. And that means, what do we get in the transformation of the semi-norm, where we look at the else derivative here? We get the whole thing here squared. So we get hk to the minus 2l. So this is this and this. And then we get, in addition, the determinant, which is 1 over hk to minus 1. So we get this factor here in. So what does that mean? And now we can really do all the derivatives from 0 to k. From 0 to k plus 1. In the end, k plus 1, we don't have an order estimate, but we can do, of course, include it. We go through all the derivatives from 0 to k plus 1. And changing from the m norm at k to the m norm at k hat squared just means to bring in this factor here. So now we need an estimate for this quantity here. So now we are the reference element. Now we want to do the estimate on the reference element. So we want to estimate this quantity by some constant, some generic constant, times the h hat. Okay, the h hat is 1 here. To some power, still 1. Times, and now it becomes important, the k plus first semi-norm of the v hat. So how can we do that? And then if we have this, we can go on. Let me first claim we can do that. Let me first claim then we can find a constant c such we can estimate this quantity here. So we go now higher in the norm, in principle, but we only want to have here the semi-norm, the k plus first semi-norm. So in the m equals k plus first, this is a sort of a trivial estimate, as we will see, but in the other cases it is not. But let's assume that we could do that. Now we have to do the final step, namely go back from the reference element to the general element. What does that mean? So I skip this for a moment, how we do this then later on. So, okay, we were here then. We would be here then at this level here. Here everything is squared, therefore here the norm squared, and you see all the constants always are denoted by c. If I square a constant, it's again c, and so on, to reduce a little bit the notation. So what I do with this term, now we do the transformation back, and going back means we get now corresponding, we do not get corresponding powers of 1 over hk, but we get corresponding powers of hk. And what do we get? So from here we had 1 minus 2m, that is what we had already, and going back we get correspondingly 2, so this is the 2 from here. Well, what is the m? The m is now k plus 1. 2 times k plus 1 minus 1. So the 1 from here and the 1 from here cancel. So this will be also in the general case. The factor which comes over the determinant cancels. Because once it comes as determinant, and going back it comes as 1 over determinant, or determinant of the inverse matrix. And that is one thing. And now these two things here go together with the m. So what do we have left? We have now here 2 k plus 1, in brackets, k plus 1 minus m. And as long as the m is less or equal to k, we have gained something. So we have still a positive power of hk. So now we put the whole thing, that was on the element. Now we put the whole thing together again. So we sum over all the elements. So let's first do for the, there are two situations. So either we are in a situation where the functions which appear here, the functions we approximate and the interpolant, are in the full space which is required here, so in the HM space. Then, of course, these semi-norms on the full on the element go together to the semi-norm squared always on the full space. So this is the case for m equal to 0, just for the L2 norms, and m equal to 1 because we know everything is in H1. It would not be the case in general for H2, H3, and so on. In this case, we would have sticked to the sum over those squares of norms on the small elements. One also then speaks of broken Sobolev spaces in this case. We cannot apply the full Sobolev norm because the function is not in the corresponding Sobolev space. It's only restricted to certain subdomains, only restricted to the elements. It's in the Sobolev space. For example, take the piecewise linears from the P1 approach on the triangles. They are in H1 because they're continuous functions. They're not in H2 because the derivatives are not continuous. So it does not make sense to speak of an H2 functions of the H2 norm of this function. But on each element, which is where we just have polynomials, of course we can apply the H2 norms. And if we put these together, then we have a broken H2 norm. Okay, but in these norms where we are interested in particular the H1 norm, of course this fits together by summing up. So here we then really get the H1 norm squared function minus interpolant. That is the one thing. Correspondingly, we have to add up the right-hand side. And this we can do, for example, as I said, by just estimating the hk by the maximum of all them, by h. Then this factor goes out of the sum, and then there is the sum of the corresponding semi-norms here. And if we now say, okay, we have a function of this regularity, then this adds up again to the square of the semi-norm. You see the difference. For the V, later on our finite element solution, we have a certain degree of freedom in the assumption. When we say, okay, I take the liberty to assume that my solution has this and this regularity, then, okay, it has this regularity. Maybe it's not it's a much too strong statement and we miss all the important cases, but it's legitimate to do so. The element of the ansatz space has a certain regularity and we have no influence on that. If we say we have linears on triangles, then we know this is an H1 function but not an H2 function, and we cannot, also by assuming, we cannot change this. So let's summarize what we have seen in the one-dimensional case. So we have shown with this big gap in the middle of the proof still, we have shown if we consider one space dimension, omega equals an interval HP, we use Lagrange element with polynomial ansatz. And okay, now you will wonder, okay, where does the element come in? Which kind of elements we use? And where does the power come from? Where does the power k, why does the power k come in? And now, of course, the element has to play in. This we will see in this middle part of the proof, which is still missing. In the middle part, we will see this power k, which appears here as k plus 1, and which appears here in the range from 0 to k plus 1, is related to the method by the requirement that the polynomial space pk must be a subset of the ansatz space. Under this assumption, we will see in a second, we can fill this gap in the proof. And this makes sense. The higher we go here with the k, of course, the more effort we have to do. and the more benefit we expect, the higher the order we expect. And then it's reflected here with the higher the order we get. So if this is the case, there is a global constant C that for all functions v of hk plus 1, we can estimate. So what do we estimate? We estimate such a broken Sobolev norm. It's, so to speak, the broken Sobolev norm of order m ranging from 0 to k plus 1. In the case m equals to 0 and equals to 1, we can just write the normal Sobolev norm, just writing v minus ih of v in the 0 or 1 norm. We can estimate this norm by the constant times h to the power k plus 1 minus m times this highest order semi-norm. So what does, for example, let's look at our most simple case, k equals to 1, linear Ansatz head functions. In the k equals to 1 case, this says, if we are sure that the functions we are going to approximate is in h2, we can estimate the deviation in the h1 norm by 2 plus 1 minus 1. So we get the power h to the 1, linear convergence. If we would invest more, if we would have invest here P2, we take quadratic ansatz, we get here a power correspondingly for the h1 norm, we get here h squared. But only if our function we are going to approximate is in h3. In the other case, we can only then use this other estimate, and we stick to the power h. That is what we have discussed last time in comparison. Is it reasonable to use, say, linear ansatz space or use quadratic ansatz space? In which case is it reasonable? So that is now the estimate for the approximation error. But by Sayre's lemma, we know that the approximation error is just an upper bound up to a constant of the error of the finite element error. So in the end, we also have the following order of convergence result. If the solution of the boundary value problem is in hk plus 1, then in the 1 norm, in the h1 norm, we have the estimate of the solution and the finite element approximation in terms of c hk. So this is the situation here. M equals to 1 here, hk, and here times the k plus 1 semi-norm. So again, we see here order 1 for linear ansatz, order 2 for quadratic ansatz, and so on. But only if the solution has the corresponding regularity. And now, this is a principle I also said already. Okay, this tells us more. This tells us also something about the case m equals to 0, about the L2 norm. This tells us in the L2 norm, we get a power more. In the L2 norm, we have k plus 1. This is very tempting now to say, okay, the finite element method is, with linears, is in the error measured in the L2 norm, does not only have the order of convergence h, but h squared. Under certain assumptions, this assertion is correct, but the argument is wrong, because I have no direct relation in the L2 norm between the approximation error and the finite element error. I have no Sayre's lemma in the L2 norm. So now we have to fill the gap in this proof. Okay, so we have to prove this assertion here. In one space dimension, we could prove this directly, but we will do a proof which is general and which goes over to multi-space dimension. And the argument is the following. Look at this operator capital G, which goes from hk plus 1 to hm. So we go down in the order. What do? We just take the function which appears here. So this is just the identity, or more precisely the embedding, because we go down in the order. And this is the interpolation operator. So first of all, this is a linear operator here. But it's not only linear, it's also a continuous operator. For the first part, this is clear because we go down in the amount of derivatives we are looking at. And now let's look at the interpolation part. So what can we do? We are on the reference element. We write down the interpolation operator explicitly. So we have those shape functions and we have the corresponding values. So first of all, of course, we can go down from m to k plus 1. This is a trivial step. We lose some orders here. Now we use the triangle inequality, so we get sum over the norms of the f heads, let's say, times the modulus of those coefficients. But those coefficients, the values at the nodal points, again, can be estimated by the infinity norm, as long as this makes sense, as long as the nodal values make sense. But this we have assured by having assumptions which make clear, with this assumption being element of hk plus 1, that our functions we are dealing with are continuous functions. So then, of course, the value can be estimated by the maximum norm. So we have this situation here. Okay, so we have here a certain factor which is just, it can be viewed as a fixed number. Well, that's now this situation with variable terms and fixed terms. So the L is a fixed number, the basis functions are fixed, the reference element is fixed, the K is fixed here as a maximal value. So of course from all these quantities this constant becomes dependent, but if we allow for this dependency then it's a constant. And now what do we do with the infinity norm? Here we use now the continuous embedding to the Vk plus 1. And that is now, I think, as far as I see, the only place where we would have changed the situation a little bit if we would have Hermitian elements. In the case of Hermitian elements, we would have had here not function values, but values of derivatives. So we would have here a maximum norm of derivatives, and we would have had enough regularity that still there is, so to speak, an embedding of the corresponding derivative to the continuous function. So we would need more regularity on the solution. A part of this, the whole argument is the same for Hermitian elements. Okay, so what do we have here? We have here an operator which is linear and continuous. And what do we want to have of this operator? Yeah, what does that mean? Continuity means boundedness. That means that the that the corresponding M norm of this operator, so of the operator G of V hat, can be estimated by a constant times the k plus 1 norm, but the full k plus 1 norm. And what do we want to have? We only want to have here the semi-norm. So this argument up till now applied to any linear continuous operator. So this operator has to have something which allows us to have this boundedness estimate, maybe to the expense of enlarging the constant to some expense, to only have the highest order semi-norms. And in this sense, it's a little bit similar to the Poincaré inequality. In the Poincaré inequality, we said, okay, there are certain norms we can estimate. For example, what does the Poincaré inequality say? It says us the L2 norm, of course, can trivially estimate it by the full H1 norm. But it can also, and that is the Poincaré inequality, then we can estimate it by the H1 semi-norm if, which is wrong in general, if the function is 0 at the boundary or the part of the boundary. So we need here further properties of this kind of thing. And the property which we need, and which we have, is the situation that the full ansatz, that the full polynomial space pk is in the kernel of G. The G of P is 0 for every P of the polynomials of degree k. Why is this? And here now the assumption comes in that the ansatz space is such that it contains the full space pk. And now, having an element of this type, you have an element from the ansatz space, but the ansatz space, of course, is exactly interpolated, so this thing is the same as this, and then, of course, G of this quantity is 0. So this property we are now going to use, and we are using this by using the so-called Prembl-Hilbert lemma. So the Hilbert is not the Hilbert you think. It's not David Hilbert. It's a much younger Hilbert. I forgot the first name. It's American. I guess it was a PhD student probably of Prembl. Prembl is the much more well-known name in this business. In any case, it's not David Hilbert. What does the Prembl-Hilbert lemma tells us? We will not look at the proof, but only look at the statement. It says, if I have a bounded domain, I have some k from the naturals, including the 0. We formulate it a little bit more general here for further use, not only for the HK Sobolev spaces, but for the WKP Sobolev spaces, so where the derivatives are not in L2, but in LP. So we have a P from 1 to infinity, so also the extreme cases can be included. And we look at an operator G going from WK plus 1 P to the real. So it's linear, it's a functional, in fact. Here on top we did not have a functional, so this will require a certain further consideration how to apply this lemma. Alternatively, one could have formulated also the lemma for operators, so that there's not much difference in these two things. So here we are talking only about functionals. These functionals are supposed to be continuous and linear. That is what we checked for our operator, a part of being a functional, of course. And with the requirement that the pk, the polynomial space pk, belongs to the kernel. That is also what we checked. And the assertion of the lemma is then there is a constant independent of the operator, such that for every v from the Sobolev space, we can estimate the modulus of gv. So what could we do? What would us the boundedness, the continuity to give? It would us tell us we can estimate the gv in modulus by the norm of g, the operator norm, the induced operator norm, times the full norm of this space. So if I take here 2 bars, not only taking the k plus first order derivative, but all derivatives up to order k plus 1, then this is a trivial statement with c equal to 1. And the real statement is I can allow here only for the highest order Sermin norm, maybe by increasing a little bit here the constant by a factor c. So how to apply this now to our situation? Our situation is not, we are not in the situation of a functional, so we have to relate to functionals. So we have the general situation that the HM norm as any norm in a normed space, or in a Banach space, at least in a Banach space, can be expressed in the following way. Take any linear continuous functional phi on this space. So this is denoted here with this notation. So the dash means we look at all the linear continuous functionals at the topological dual of the space. We take those which have operator norm less or equal to 1, and then we evaluate those functionals at this vector w hat, and then we take the supremum over those values. Just wondering whether a modulus is missing here. Possibly a modulus is missing here, but I think in the end it's the same which comes out. Those of you who had a course in functional analysis maybe have seen this relation or not. So maybe we relate it a little bit. What does it mean? What do we do? What do we have? So we have an underlying space here. Call it V, say, neutrally. Then we have the dual space, V prime. Then we have the dual space of the dual space, V prime prime. And as you might remember, there's always an embedding from V to V double prime, just by this mapping. So what is the linear mapping which is defined on the dual space? For a given element of the basic space, we just evaluate the functionals at those value. And what this statement says is that this mapping is isometric. I get the same norm if I take the norm in the starting space, or what I have here is just the induced operator norm of this evaluation functional. I think as we are here in the reals, we can omit here the modulus. We can absorb the modulus in the phi. Okay, so this is what we are going to use. And now to use this in the following way, we have our operator G, and we take any fixed linear continuous functional on HMK hat, and we look at this composition G tilde, just the functional phi composed with the operator G. Now this composition is again linear, and it's now not only a linear function, it's a continuous function, because both parts are continuous. Then, of course, both parts can be estimated. So what can I do? I can get the norm here, and I get the norm from G, and the norm of G, that is something which I have computed. I get a 1 here from this contribution, and I get a C, let's say C bar term, if this I call this here C bar from this contribution. So I have here some constant from the norm of G, and I get some constant from the norm of phi. So, okay, this is just composition of continuous operators is continuous, nothing more than that. So this is now a functional to which I can apply the Bramble-Hilbert lemma. What does that mean? It tells us there is a constant C independent of phi, that is of importance, and independent of G, such that now I get the same estimate. Now on top I get this further constant here, and I go down here to the semi-norm. Okay, this is the G tilde. This is the phi of G. But if I look at the supremum of all those quantities with phi's with norm less or equal to 1, I come back to my norm of, in this case, of the G of V hat, and so I come back here to the estimate I would like to say. So this term goes out because I now take just the supremum over all phi's with norm of phi less or equal to 1. So this goes out by 1, and then by the starting point we had, this supremum is just this quantity here. Of course, you see this argument could have been done also in general directly to the Bramble-Hilbert lemma, and could have led to a statement of the Bramble-Hilbert lemma, not for functionals, but for operators. That's no difference to do it in one or the other way. Yeah, and how to continue now with this estimate on the reference level we have seen already. So this concludes now the proof in the one-dimensional case, first of all for the approximation error, and specifically applied for m equal to 1, it leads us, together with Sear's lemma, it gives us the order of convergence estimate as discussed. Okay. In this one dimension, this proof actually is not necessary. A more direct proof is possible, but this is only the starting point to have something to generalize to multi-dimensions. So let's see a few variations which we have here if we now go to the d-dimensional situation. In the one-dimensional situation, it was simple in the sense that this transformations of the x to the x hat derivatives just gave us powers of h, which we could put back and forth as powers of h or powers of 1 over h. It was an identity. In a multidimensional situation, we only have estimates, and we see that some actually a little bit other parameters come in, not directly the age. So what now comes in is not only the size of the element, but the shape of the element. In 1D, okay, there's not much variation in the shape of the element. In 2D and in 3D, of course, it is. There are flat triangles, there are not so flat triangles, and that will play a role. Okay, so let's look at the norms. So we have to look again at the semi-norm here in the k element, in the x derivative. So with this quantity, if we look at the square, we have this quantity here. Again, we do the transformation. So we know already, have seen this quite a bit, what comes out. So we get the modulus of the determinant by the transformation of the integration element, and by the transformation of the derivative, we get here the b to the minus t, and here we get, again, we get the b to the minus t. And now, okay, let's first think of the Euclidean norm. So we have vectors here. So let's first think of which I have a Euclidean scalar product here. So let us first think of the Euclidean norm and correspondingly of the induced matrix norm, that is the spectral norm. Taking these norms, of course, we can estimate what we have here by, this is Cauchy-Schwarz, Euclidean norm times Euclidean norm, and then in a further step by norm of b to the minus t times Euclidean norm times norm p to the minus t times Euclidean norm. And in the spectral norm, a matrix has the same norm as its transpose. Because if I have a matrix A and I look at A transpose A on the one hand side and A transpose at the other side, these two matrices have the same eigenvalues. Remember? Any case, check it. Okay, so for the Euclidean norm, for the spectral norm, that means we can forget about the t. Of course, we have the inverse still remains. So we get this estimate in the spectral norm with a constant c. But now we can say, as now this fixedness argument comes, we are here in a finite dimensional case. The dimension is just given by d, by our spatial dimension. So we're talking here about 2 by 2 or 3 by 3 matrices. We can take any other matrix norm to the expense of a fixed factor here. So if we allow for a constant here, we can take here any norm. And thus we will take advantage of this, taking different matrix norms then. Okay, so this is the one direction in the one. So what we get, so to speak, in the one-dimensional case, you see, in the one-dimensional case, we would have got here something like h to the minus 1, and here correspondingly h, now we get here the inverse of the matrix B, which is a little bit something different. And correspondingly, if we go in the other direction, if we, so to speak, reverse the roles of k and k hat, then, of course, what was B becomes b to the minus 1, and we get correspondingly the same estimate, now with b instead of the b to the minus 1, and 1 over the determinant instead of the determinant. So we don't have equalities anymore, we have inequalities. That's not so much the point. We have the determinant factors, and you see, if we, so to speak, first do this estimate, because we start here from a general element and go to the reference element, and when we do an estimate of this type, because we want to go back from the reference element to the general elements, we go this factor in, we go this factor in, this cancels again. This is exactly as this factor which came in from the determinant in the one-dimensional case. But the factors which we have to deal are apparently those quantities which then come in from powers of p to the minus 1 times powers of p. So this we have to relate to the geometric quantity h. Okay, before doing so, what we have proven here for the simple case, let's just state the corresponding statement without proof for, first of all, now for higher order derivatives and for other and for more general Sobolev norms. So okay, the situation is the following. We have two domains, k and k hat, bounded domains in Rd. We have an affine linear mapping which bijectively maps the k hat to the k. And now we compare on the one hand side the elements V from the Sobolev space WLPK, and on the other hand V hat WLPK hat. So it's more general because the L is now a natural number, not only one, and we have here a P instead of the 2. But the estimate which comes out here is exactly the same estimate as we have seen. Going to the reference element, we can estimate now by a constant the Lth power of P. So here the amount of derivatives comes in. The determinant now not to the minus 1/2, to the minus 1 over P times the corresponding semi-norm on K. And if we go back, P is exchanged by P minus 1, and here the sign in the power changes, as we have seen. So we have different powers of the P and different powers of the P minus 1, which we have to relate to each other. So, and for this we now need two basic geometric quantities which characterize an element, and then in total the overall triangulation. The one quantity we have introduced already, that is the hk, the diameter of the element, the maximal distance we can have looking at two arbitrary points in the element. In a triangle, that would be just the length of the maximal edge. And the other quantity, that is what we call hk. And the other quantity is the quantity rho k. That is the supremum over all diameters, diameter exactly in the same sense as I just used it, but now of balls which are subsets of the element. So in terms of the triangle, the rho k is just the diameter of the what is called the incircle, the Inkreis des Dreiecks. And you see, so what do we do? And you see the situation is as follows. For example, if I look at this element, and I do this process here. You see the maximal length more or less stays the same. I should have made it a little bit larger here, really that it stays the same. The maximal length of the edge more or less stays the same. So hk is more or less constant. But what happens to the incircle? This is not well drawn here. Of course, this rho k gets smaller and smaller. So rho k goes to 0. So you need to it will turn out that this situation will not be allowed, which is bad because this reflects a quite reasonable refinement strategy. So, okay, we will come to that. So again, let's try to understand what that means. We will have to have conditions relating the hk to the rho k, but not for a fixed triangulation, but for a sequence of triangulation. So these are elements not of one triangulation, but of a sequence of triangulation. So I have here an H1, H2, H3, or let me maybe index it here on top. Looks maybe a little bit better. Because if I would only look at one fixed triangulation, of course I would have a finite number of elements. And for a finite number of quantities, I always have a lower and upper bound of certain quotients. That is not the question. The question is what happens for H2 0. So these two quantities, with these two quantities we will work now, and we will see how they appear in the estimates of those norms of the matrix B. Okay. This we have computed already. H hat is square root of 2. And if you check this, what I claim here, the in-circle diameter is 2 minus square root of 2. It should be elementary geometry. Okay, now the claim is the following. If we now look at the spectral norm, then the spectral norm of the B matrix can be estimated by hk, the diameter of the element, over the row of the reference element. This is a fixed quantity, so we get here an hk. This is good because we would like to see powers of hk in the estimate. But the corresponding norm of the inverse matrix, and now you just have to reverse here the situation, and meaning you have to reverse the roles of the elements. That means from the hk becomes the h hat, something fixed, and the rho hat becomes the rho k, something variable. And now we have 1 over, so this is now the important thing, 1 over the rho k here. So we only have to prove one of these estimates, say the left one, and let's do so. It's not very complicated. Okay, so what is the spectral norm? Spectral norm is the norm induced by the Euclidean norm. What does that mean? We take the supremum over the unit ball, take the images of the elements of the unit ball, and then take the Euclidean norm of those images. That's the definition of the induced norm. What do I do here? I do not take the unit ball. I take the ball with the radius rho hat. But then I subdivide those elements by rho hat. So I get elements at the surface of... I do not take the surface of the unit ball, but the surface of the ball with the radius rho hat. But by the subdivision, I go back to the surface of the unit ball, and I also get all the elements at the surface of the unit ball. So that's a proper representation of all the elements at the corresponding sphere. So what do I do with this constant? I get it out of the linear operator of the norm of the supremum. So this quantity is left here. So now, what does it mean to have this quantity rho hat? This is now, by definition, the supremum of all those diameters of balls inscribed into into the set, in this case into k hat. So either by an approximation process or directly, we could now argue as follows. Okay, we have let's assume that the supremum is a maximum. Then I can simplify a little bit the argument. That means I have my reference element, or any element. Then I have here my ball inscribed, and this ball has the diameter rho hat. I have here a certain middle point. Let's call it M. And then what I have with the psi, I have with the psi a vector with a Euclidean length rho hat. So if I now do the following construction, if I look at 2 points, they are called y hat and z hat. And let's say we take the middle point plus the rho hat, and the middle point rho hat half, and the middle point plus rho hat half. Then both of these points, by definition of a ball, have to be in this ball. Actually, they are at the boundary, but that we don't even use. What does that mean for the connecting vector for these 2 points? Yeah, the connecting vector is just the other direction, minus z. So what I do, I go here, I take this direction, I go from this point to this point, I go from this point to this point here. The connecting vector is rho hat, and that is the statement. I can, for any of these, that is only a length. I'm a little bit confused now. I have to distinguish between the rho hat and the corresponding vector. That is not the rho hat, that is just the length. That is the vector psi. That is the vector. Okay. This whole thing here has the length rho hat. Now I have a vector psi of this length. So, and here I get the vector psi back. And now if I look here, what is, I see I'm on the ball here, actually at the boundary of the ball. Okay, what does that mean? I can represent the psi in terms of this difference. The b of psi is the difference of the corresponding f values. The constant drops out. So the fy minus the fz. Because I'm here with those 2 points, I'm in the ball, I'm in the reference element. With the corresponding images, I'm in the general element, k. That means the distance of these 2 points can be only the maximal distance. So the Euclidean norm of this bxi has to be estimated by hk. Okay, so what does that mean? All this stuff here can estimate by hk, and I'm at this estimate which I would like to see hk over rho hat, and correspondingly then for the inverse. Okay. What does that, maybe I don't have too much time anymore. Now let's see what that means now for the multidimensional estimate for the approximation error. So what do? We first go from the reference element, from the general element to the reference element. So this is the estimate of this type here. So we get powers of b in. Getting powers of b in means we get powers of hk in. Then we have via Bramble-Hilbert, we know on the reference element everything is okay. We have this estimate we would like to see. Then we have still this highest order seminorm on the reference element. We have to go back. To go back now means we apply this estimate. And by this we get powers of b to the minus 1 in. Powers of b to the minus 1 in the corresponding norms gives us, we now get powers of 1 over rho in. That is now the distinction between h and rho. In the one-dimensional case we have h equals rho. And this is then what comes out if one really looks carefully at the estimates. So we get from the first, let me see what it is. From the first step, we get k plus 1 h powers in. And from the other step, we get m1 over rho k powers in. And now I take here hk powers in addition, m pieces, and I have to take that away here again. And now I see this term is exactly the term we have seen before in the one-dimensional case. But now this term is here in addition. In one dimension, this term does not exist because hk equals rho k. But now, of course, that this estimate is not destroyed, this quantity has to be bounded. Or at least, if it's not bounded, it has behaved well, and then it will destroy at least maybe a little bit of the order of convergence. But if you really want to gain the full order of convergence by this type of proof, then this thing has to be bounded. That means we have to assume that there is a constant which is called sigma, such that for all triangulations in our family and for all elements, the rho k can be estimated from below by sigma times hk. That is, this quotient which we had there, what was the quotient? Let's go back. hk over rho k can be bounded from above by some constant. Here in this notation it's 1 over sigma. So we are not allowed to do things like that. We are not allowed to make the rho smaller and smaller, what happens here, without making the h correspondingly smaller and smaller. So if we would allow for this type of elements, which we have to do another proof. It's not said it's impossible, but it's not included in this proof. So this condition is a certain requirement on a family of triangulations called regularity, or shape regular, so form regulaire. So a family of triangulation is called shape regular if there is such a constant such that for all age and for all elements of the triangulations we have this type of estimate. Having this type of estimate, this is a constant, and we gain exactly the order of convergence for the approximation error we had seen before. And as a consequence of that, we gain exactly the same error estimates in the H1 norm as we have seen before. We could relax the situation a little bit and could say, okay, we don't have an estimate of this type, we only have an estimate of this type. Not hk, but hk to the power 1 plus alpha. That means a certain negative power of h. We can estimate this term here, but not by a constant, but by a certain negative power of alpha. So we get here of h. So we get here something, a negative power in h, which, so to speak, reduces this order. If this reduction is not large enough, then we still keep a reduced form of convergence. So this would be a sort of a relaxation of this result. But the standard assumption is this shape regularity of the triangulation. Okay, the question now is, the non-pleasant, so this is now quite a strong result. The non-pleasant thing is that actually one would like to have elements like this. Think of say a laminated domain which has a very thin layer here in between. And if we would now refine, of course, what we would like to do and what the situation is, we can imagine that the variations in this direction are much stronger than the variations in this direction, because here we have let's say a conductivity K1, we have here a K2, let's say much larger K1, so this is an insulator built in. Here we have K1 again, something like that. So what we'd like to see today, we would like to do very many elements here, and maybe not so many here. And if we don't, okay, we could now take these rectangles, or we could also take our Friedrich-Scalar elements, but that would really mean we run into this type of elements. And at the moment, it is said this type of refinement is not allowed. We will look at this situation, so two-dimensional rectangles or parallelograms, and correspondingly in 3 dimension, and the triangle situation we will look in more detail, and we will see then a little bit weakened conditions. So the condition which comes up here is a little bit too strong for these special cases, or there are different, more appropriate conditions, and this we will then see next time.